From Diamond Light Source, this is the Diamond Podcast.
Hello, and welcome to the Diamond Light Source Podcast, where we take a look at the latest science from the UK's National Synchrotron facility. In this edition of the podcast, we're peering into the minuscule world of nanoscience to find out how something as big as diamond can look into the world of science on a scale as small as the nanoscale. We'll be hearing the latest news from Diamond, including the opening of 2 new beamlines. And delving into the nano world, we'll be hearing about a new way to read and store data that could revolutionise computers, sound systems, and pretty much anything else that requires a hard drive.
The problem with hard disks is they contain moving parts. So you have to, if you're not going to have any moving parts, then the only thing you're allowed to move is the information itself. If you can visualise this magnetic structure, you would turn on the current and you would see all these little regions travelling along, kind of like a train, blown along by this wind of electrons.
And moving from computers to chemical reactions, we'll be finding out how the byproduct of a species of bacteria could help industry become a lot greener.
Currently in industry, if you make magnetite or cobalt ferrite, I believe you make it at very high temperatures, whereas the bacteria, they're providing the energy to the system. So we think this is a more environmentally friendly route, and they might actually make the nanoparticles better than industry as well.
But just how do these bacteria actually produce the particles that we want? I'm Mira Senthilingam, and this is the Diamond Light Source Podcast.
The Diamond Podcast. For more information, look us up online at diamond.ac.uk/podcast.
Before we delve into the tiny world of nanoscience, let's join Sarah Bucknell from Diamond's communications team to find out what Diamond's been up to in recent months. So firstly, Sarah, 2 new beamlines have come into operation.
Recently, we had first light on 2 of our Phase 2 beamlines. That means it's the first time we got synchrotron light into the optics hutch on each beamline. They were IO7, the surface and interface diffraction beamline, and I12, the joint engineering, environmental and processing beamline.
Now, what will both of these beamlines be looking at?
IO7 will use high-resolution X-rays to investigate the structure of surfaces and interfaces under different environmental conditions. And I12 is a multi-purpose beamline used by practitioners in engineering, materials science, imaging, process engineering and earth sciences. It's really exciting when we get the beam of synchrotron light to the beamline for the first time, because it confirms that what we've built is working, and it means that we're not far off from welcoming the first users, and we're hoping to get them to IO7 and I12 by the end of 2009.
Now, when did these beamlines achieve first light then?
Well, it was Tuesday the 12th of May, and it's the first time 2 beamlines have achieved first light on the same day. But it's not surprising, really, because it's a really busy year for Diamond. We've got 5 experimental stations coming online this year, and that will bring the total of operational beamlines to 18. And this keeps us right on track to complete Phase 2 by 2012, and at that point we'll have 22 beamlines in operation.
OK, so 5 more beamlines are being developed, and the first one opened 2.5 years ago. So good science has been taking place here for quite a while now, and papers are being published as a result.
That's right. As you say, our Phase 1 beamlines have been operational now since January 2007, so we're starting to get some high-impact publications. And we've had some recent published papers in Science and Physical Review B, featuring research from our Extreme Conditions beamline I15. That's a science paper, and that was on how earthquake waves travel through the Earth. And then the Physical Review B paper was from our nanoscience beamline IO6, and there'll be more on that later with Chris Marrows.
So as well as the science, you've also had a few interesting visits recently.
Yes, we had another royal visit back in April. We had a visit from the Duke of York, Prince Andrew. Whilst he was here, he met the finalists of the National Science Competition. This was a contest for 13 to 19-year-olds to become the Young Scientist or the Young Technologist of the Year.
And so did the finalists get to meet Prince Andrew?
Yes, well, part of the finalist prize was a visit to Diamond. So we organised for their visit to take place on the same day as Prince Andrew's. And they thoroughly enjoyed the opportunity to see the facility and to meet our scientists and engineers. And it was definitely a bonus to get to meet the Duke of York as well. We really enjoyed welcoming the finalists, and it was great to help encourage them into careers into science and engineering.
Well, you also had your Inside Diamond Day recently, so how did that go?
Yes, that went really well. It was on Saturday, the 23rd of May, and over 200 people came. This time we targeted those who are into the arts by featuring the event as part of Art Weeks, which is a festival of visual art running throughout Oxfordshire. It was really nice to welcome the Art Week's audience and talk to them about science. And so that went really well. The next Inside Diamond is on Saturday, 3rd of October, and once again you'll be able to register via our website.
Now, the science that happens at Diamond isn't possible without its users, so you're now actually setting up a committee to help your users here.
That's right. Diamond is really keen to listen to its users and provide them with a platform for dialogue so that we can work with them to get the best out of the facility. So the Diamond User Committee launches on the 23rd of June. This is an opportunity for users to tell us what it is that they want from Diamond. If anybody is interested in finding out more about this, then they can email dlsinquiries@diamond.ac.uk.
So as well as this, are there other events taking place over the summer?
Yes, there's going to be lots of specialist science workshops at Diamond throughout the summer. And then in September, we've got a major international conference on small angle scattering. More details on all of these and the latest information can be found on our website.
Now, something exciting coming up this summer as well is the World Conference of Science Journalists. So how's Diamond getting involved with that?
Well, Diamond is involved in a number of ways. We're taking part in the official welcome reception, which is at the conference venue on Tuesday, 30th of June. And there will also be a press briefing on the Thursday at the French Embassy, and that's with some of our fellow European light sources. And then after the conference, we'll be hosting some visits on the Friday, along with other Oxfordshire science facilities, JET, ISIS and the Central Laser Facility. And as well as all this, there'll be an international meeting of light source communicators on the Friday. It's going to be a really busy week because as well as the World Conference, at the same time we've got one of our science and art projects, Designs for Life, at the Royal Society Summer Exhibition. So there's lots going on to keep us all busy.
Thanks, Sarah. Diamond's Sarah Bucknell, who'll be back with more of the latest news from Diamond in the next podcast. Now, this month, we're finding out how Diamond is helping scientists investigate the nano world. So now, we hear from Sanjeet Desi, Principal Beamline Scientist on Diamond's Nanoscience Beamline, to find out a bit more about just what nanoscience is.
Well, I guess nanoscience is about understanding and manipulating materials at the atomic level. Well, in a nutshell, I think materials are profoundly affected by quantum mechanics as you scale them down to the nanoscale. And this means that a material that is an insulator normally become a conductor down at the nanoscale, or a material that is opaque in the macroscopic world can become transparent. So it's all about engineering materials so that they have different properties when they are scaled down to the nanoscale.
Just how small is the nanoscale?
Well, the nanoscale is down at the atomic level. The nano part of the word means a billionth of a metre. So a billionth of a metre is round about 10 atoms wide. So it really is down at the atomic scale of matter.
And why is it important to understand things on this scale? I mean, what kind of things can you learn?
Well, in my particular case, I try to understand magnetism, and magnetism is very important for hard disks. The reason why we've gone from a room that holds a few sheets of paper of information to iPods and hard disks that store thousands of songs and movie clips is because the magnetic particles that store the information in a hard disk have got smaller and smaller. And nowadays they're only a few nanometers wide. And it's by understanding how these magnetic materials behave down at the nanoscale that we can improve magnetic disks, for instance. But that's my particular area. There are all kinds of areas where materials are used down at the nanoscale. Sun cream, for instance, and paints and pigments all contain nanoparticles that give them the properties that they have.
So why does something as big as the Diamond synchrotron need to be used to look at things on this small scale? How is synchrotron light focused down to look at these?
Well, Diamond produces very intense rays of X-rays, and we use these X-rays to understand materials at the nanoscale. So, for instance, on my instrument, we use the X-rays to illuminate the sample, and this ejects electrons from the sample, and those electrons are then used as an electron microscope to image the material and find out the properties of the material.
So we're actually located down by your beamline now. So which beamline is this, and what is this large machine in front of us that is almost the same size as a tractor, and yet it's looking at things on the nanoscale?
Well, this is the Nanoscience beamline. This is called a photoemission electron microscope, also known as a beam. So the electrons are ejected from the sample by the X-rays, and then we use a series of electron lenses that we can see in front of us over here to focus and project the electrons onto a detector where we form a very detailed image of the surface. And by doing this, we can find out lots of interesting things about materials. And the very nice thing about X-rays is that we can choose the X-ray energy to be sensitive to particular elements within a sample. So if we've got a material made up of lots of different elements, we can study each element of the material.
At the same time?
At the same time, yes. And through this, we can understand if one part of the material is behaving in the right way or the wrong way, and what we might need to do to the material to improve it.
So do the X-rays just come straight out of the synchrotron and just into this electron microscope? I mean, what happens in between?
Well, the X-rays are generated about 50 metres away from here, and the X-rays, although they're very, very small, they're about the tenth of the width of your hair, they're still diverging a bit like light from a torch. So if we let that X-ray light diverge all the way down here, it would be very big by the time it got to our microscope. So along this beam line, we have a series of mirrors that focus the X-rays and allow a very, very high-intensity spot to be generated within the microscope.
What kind of experiments are taking place here, and what are the potential applications of these?
Well, on this beamline, we concentrate quite a lot on magnetism. So we study a branch of physics called spintronics. We all know about electronics, where we exploit the charge of the electron. But in the past couple of decades, there's a new emerging technology called spintronics, where we also exploit the spin of the electron. And this beamline is very good at understanding the fundamental aspects of the spin of an electron in a material. For instance, we might use the chemical-specific nature of the X-rays to study two sides of an interface of magnetic material, of two magnetic materials. So we tune the X-ray energy to study the one part of the interface and understand the magnetism on that side, and then we tune the energy of the X-rays to another material and understand the magnetic material on the other side of the interface. So we really try to understand something about the magnetic glue that bonds these materials together. And that's really crucially important in terms of hard disks and the sensors that are used inside them to detect the tiny magnetism that is coming off these nanoparticles that are used in hard disks these days.
But it seems like it would be quite a versatile machine, so can other things as well as spintronics be looked into?
Yes, it's very versatile, and we've got a very vibrant community of researchers that are always coming up with new and novel materials that are just ideal to be studied here at Diamond with this instrument. And because we've got a synchrotron source over here that's not a continuous source, it's a pulsed source, it's almost like a laser source, we can use that pulsed nature of the X-rays to do timing experiments. So we can study materials and what happens to them down to a millionth of a second. In addition, continuing the theme of, say, spintronics, we can look at magnetic domains and see how an electrical current can move those domains and how those magnetic domains can be manipulated with an electrical current. So as you can see, there's a lot going on here at Diamond, and I think the future's really bright.
Diamond's principal nanoscience beamline scientist, Sanjeet Desi, explaining how the electron microscope at Diamond can help us understand more about magnetism on the nanoscale.
Did you know that Diamond's floor area is 45,000 metres squared? That's almost the same as 8 St Paul's cathedrals.
We've had an overview of the role synchrotron light can play in nanoscience research. So now we peer a little bit closer to see how something as small as a nanowire could be used to transfer data faster than the current computer hard drives we see today. Chris Marrows is working on this new field of information transfer and storage at the University of Leeds, and he explained how he's developing this technology. But to put it into perspective, he started by explaining how our current hard drives actually work.
So a hard drive, what it looks like if you open the box is a little bit like an old-fashioned record player. So you have a spinning disk that contains all the information in lots of tracks that are circular tracks, one inside the other. So rather than one big spiral like a record, there's lots of these circular tracks. And then there's a little head, we call it, which reads and writes the information sitting on the end of an arm like a record player arm. And then the information that's recorded along that track will whiz past the head as the disc spins around. And essentially what the disc is just billions and billions of tiny little magnets. And each one of them can be magnetized one way or the other. If it's pointing one way or the other, you can use that to record a digital 0 or a digital 1. So the little head can create a magnetic field and flip one of those things around to point in a certain direction to record a bit of information. And then there's a little tiny sensor that can read that back again when you want to read back the file to play your music track or look at your photo or access your bank statement or whatever it is that information represents.
So this current method of memory essentially has information stored in one place and a reader that basically will interact with it in order to try and read the information. But you're working on a new way in which information can be read and stored.
Yeah, that's right. The problem with hard disks is they contain moving parts. This disk is spinning round at thousands of revolutions a minute. Imagine keeping this head doesn't touch the disk, it has to fly just above it at a distance of only a few nanometers. The analogy that's used is keeping that head just above the disk is like flying a jet fighter an inch off the ground. It takes a phenomenal amount of engineering to do that. So somehow it works most of the time, but disk drives do fail. They're the bits that generally do fail in computers because they contain moving parts, and this is why we have to worry about backing up information and having multiple copies.
So now the way you're trying to improve this then is rather than having the information stored in a particular place, you're going to try and make it so that information basically moves around a hard drive.
Yeah, so you have to make something where if you're not going to have any moving parts, then the only thing you're allowed to move is the information itself within the structure. So there's some new physics that's been discovered in the last few years that lets you do that.
And so how is your research looking into creating this movement of information?
Maybe the best way to explain that is to think about what the information looks like. So we make what we call a magnetic nanowire. So this is a wire of magnetic material, and it may be only 10 or 100 nanometers across. And then you magnetize little regions of it, north or south, say, and those represent your bits. So as a physicist, we will call those regions domains. And then the joins between those things we call domain walls. So you can maybe think of the domains as little rooms full of magnetism pointing in a certain direction, and then the wall is the join between them. But there's nothing physical there. It's purely a magnetic structure. And then it turns out that you can move that whole thing along by you flow an electric current down the wire.
What do you mean by moving the whole thing along? So would you move the walls, essentially?
Yeah, so all the walls would move along. If you can visualize this magnetic structure, which is actually what we use the microscope at Diamond to do, then you would turn on the current and you would see all these little regions traveling along, kind of like a train. They'll all move along together because they should all be sort of blown along at the same rate by this wind of electrons that's flowing through them. So the wire sits still, but the data moves along it. And then if you're sitting by the side of the wire with some sort of sensor, you would see these things pass you, and you would get back your stream of data, which you would then convert into music or video or whatever it would be.
So by injecting an electronic current into this nanowire, are you essentially then just pushing these walls along the nanowire and therefore moving the information along this wire?
Absolutely, yeah, exactly what happens. So there's nothing physically moving except the data itself.
And then whereabouts would this data be taken in order for it to be read and therefore used?
What you would have is a little reader, something very like the head in a hard disk. You would have some little magnetic sensor just sitting by the side of the track, and it would feel the magnetic fields from each bit as they passed, and then it can convert that back into an electrical signal, and that would be then used by the computer or mobile phone or whatever it is.
So what are you currently looking into in order to develop this technology further?
We know that this physics works, but the problem that we have at the moment is we need very, very high densities of current, almost at the point where we will start to have these wires destroy themselves either by melting or just physically ripped apart by the force of so many electrons moving through them. We've got to make this work with much, much smaller currents. And so by understanding the details of how the current and the magnetism interact with each other, we have a few schemes where we think we will be able to reduce this by maybe tenfold or 100-fold.
And so what aspect of this research are you using synchrotron light to help you look at and understand?
So we've done some experiments at the nanoscience beamline at Diamond. Really, it's a microscope, and it's a microscope that lets you see magnetism. So we make our wires, we connect them up to some electrical contacts. So these things are prepared on the surface of a chip of silicon or something like that, just as the way they would be used. Then we take our chips down to Diamond, we put them in the microscope, and we shine the synchrotron X-rays on there, and we're able to visualize the magnetism in the wire. So it's seeing the structure, the domains and the domain walls that would represent the data, and then seeing the ways that it reacts when you stimulate it with electrical currents, so we can apply currents and just directly see what happens.
And so where would you say you are currently with this? So how much has been understood so far, and when do you think it will be available to use this as a form of memory?
We're trying to change the properties of the magnetic material itself by doping. So this means putting in small amounts of impurities, and they're things that the electrons can interact with. And we think if we find the right impurities, there'll be a very strong interaction, and this will mean you don't need so many electrons to get the same effect. We think within a year or two we will have found the right impurities that will give us a big improvement in terms of the level of current that we need. Then turning that into a technology that's for sale will probably take several more years.
That was Chris Marrows from the University of Leeds, explaining how he's using nanowires to develop faster, cheaper and greater information storage. Now, as well as computer technology, the nanoscience beamline can help us understand the reactions and products of bacteria. Vicky Coker is from the University of Manchester, and she's been looking at a certain species of bacteria that produce magnetic nanoparticles that are not only crucial catalysts in industrial processes, but can also be pioneered for cancer therapy and drug delivery. She explained how she's looking into this.
I am currently looking into how iron-3 reducing bacteria can produce magnetic nanoparticles such as magnetite, and how these could be used in industrial processes.
So why is it useful for these bacteria to make magnetite?
They would do it at room temperature rather than at high temperature, which is what currently happens in industrial processes. Magnetite is used in many different industries for many different applications, such as in data storage for magnetic recording media, and also in medical applications such as drug delivery.
What are these bacteria and where are they found?
These bacteria are ubiquitous in the environment. They are found below the surface in an anoxic zone where oxygen is no longer available. Instead of breathing on oxygen like me or you, they breathe and respire on oxidized minerals such as iron-3, manganese-4. They reduce these minerals by transferring electrons from organic matter to the iron-3 mineral, and in doing so they conserve energy for life, and as a byproduct of this they produce reduced minerals such as magnetite, and they happen to be in a nano form. So they're not doing it deliberately or for any gain to themselves, except to respire.
Now, what are these bacteria called?
They are iron-3 reducing bacteria. The bacterium is called Geobacter sulfur-reducens.
You say they're ubiquitous, but whereabouts are they found?
You can find them at acid mine drainage sites where you find wherever you find a high level of iron or manganese together with a high organic content. So they have both the electrons to transfer and also the iron mineral to act as the electron acceptor.
And how have you been using synchrotron light and so the nanoscience beamline at Diamond to help your research and to help you look into this?
Okay, because the nanoparticles are very small, there are only a couple of different techniques that we can use in order to analyse them. We can't just look at them in order to analyse what we've made. We use X-ray magnetic circular dichroism at the nanoscience beamline in order to determine the actual structure of the magnetite that we have formed. Magnetite, it's Fe3O4. It has one iron-2 cation for every two iron-3 cations, so it's a mixed valence iron oxide. And XMCD, the technique we use at the nanoscience beamline, is one of the only techniques that can determine how much of each of those three different iron cations we have present within our magnetite.
How is it capable of doing that? What is this technique?
It's an X-ray absorption technique. It's element specific, so you target the correct energy range for, say, iron, and then you use it to collect X-ray absorption spectra within a magnetic field parallel and anti-parallel to the beam direction. And the difference between these two X-ray absorption spectra is the X-ray magnetic circular dichroism spectra. And this reflects the structure of the material that you've probed with your X-ray beam.
So how does understanding the magnetism of these particles and of these bacteria help you understand more about how magnetite is made and how the bacteria are working?
Okay, because the bacteria are growing and they only grow magnetite within an anoxic environment, we've discovered that the amount of iron 2 within the magnetite is actually larger than you would find in a normal magnetite sample that had just been left out in air because they're grown without oxygen. And this is important because in certain different industrial applications, magnetite can be used as a remover of environmental contaminants, and it's the iron 2 within the magnetite that achieves this. And so if you have a bit more iron 2 there than you would normally have, then the magnetite is even better at its job than it would be normally. That, coupled with the fact that it's a nanoparticle, so you have a high surface area, leads to a really good product to reduce environmental contaminants such as chromium.
Now you know that these bacteria are capable of doing this, how could it be scaled up and used for industrial purposes?
Now that we know that they can do it, we've been trying to sort of apply different techniques in order to make it in large quantities, and that's really the next step. We haven't done that yet, but you would use a big bioreactor to grow up lots of bacteria, feed it with lots of iron 3 oxide, and hopefully get out loads of magnetite that could then be used.
So would the main uses of this magnetite that's made then be for reducing environmental contamination?
We've also been investigating how if you include a different transition metal other than iron, such as cobalt or nickel, into the structure of the magnetite, you can alter the magnetic properties, and that can lead to it having different uses and applications. We've been using the XMCD because it is element and site specific in order to probe the magnetite that we make that contains the cobalt and the nickel, which makes it a ferrite rather than magnetite, to see how much cobalt or nickel or manganese that we have got within the structure. And then we've done some other techniques that show that the material has altered in magnetic properties.
Are the bacteria incorporating these other transition metals into the magnetite then to make these ferrites?
They are. We weren't sure they would be able to do it because it's not something that they come across in the environment, like high amounts of iron and cobalt together. But when you feed them with an iron 3 oxide that contains cobalt co-precipitated within the structure, they will take the iron and the cobalt together and reform it into a cobalt ferrite nanoparticle.
Now, why would using these bacteria to make magnetite and these metalloids be better than the current way industry makes them?
Currently in industry, if you make magnetite or cobalt ferrite, I believe you make it at very high temperatures, whereas the bacteria, we're using them as our energy source, and so they're providing the energy to the system to change the structure of the mineral into this magnetic nanoparticle. So we think this is a more environmentally friendly route, and they might actually make the nanoparticles better than industry as well.
What are the applications of this magnetite then and the metalloids that can be made?
There are various different applications in industry for magnetic nanoparticles, such as data storage in magnetic recording media, ferrofluids for use in heat transfer, and they can also be used as catalysts. A more novel application is in different medical uses, such as in drug delivery and different imaging techniques, but these are still being investigated, and I don't think they're actually being used for this currently, but it's under research.
Vicky Coker from the University of Manchester, explaining how iron 3 reducing bacteria can produce nanoparticles that are not only crucial to industry, but are made using a more economical and environmentally friendly method. Now that's it for this edition of the Diamond Podcast, but do join us again in August when we'll be finding out how synchrotron light can be used to investigate our cultural heritage. In the meantime, if you have any questions about Diamond or the research taking place there, the email address is podcast@diamond.ac.uk. Thank you to Sarah Bucknell, Sanjeet Desi, Chris Marrows and Vicky Coker. I'm Meera Senthilingam. Thanks for listening and see you next time.
The Diamond Podcast is brought to you by Diamond Light Source and produced by thenakedscientists.com. There's more information on our website at diamond.ac.uk/podcast.